Okay, so here we are moving into the analysis of variance. This is probably one of the most popular and well-used tests in psychology research. We're going to be looking at the purpose and logic that underlies the ANOVA test. Again, that is going to be our main emphasis here, is understanding conceptually what this test is getting at and how to interpret the results. Okay, I will post materials on how to calculate an ANOVA for anybody that's interested or is moving on pursuing research methods. It's not really difficult, it's just a lot of tedious steps. Okay, we'll talk about something known as post-hoc tests. These are follow-up tests that we do after we do our ANOVA, and they give us some more detailed information about the results. And like usual, we'll always couple our hypothesis test with a measure of effect size. Okay, in this case, with an ANOVA, we have a slightly different measure of effect size that we use. And again, I'll focus sort of on what that's telling us and how to interpret that value. Okay, so let's look a little bit more at the ANOVA. Okay, the ANOVA is most commonly used when we're trying to evaluate mean differences between two or more groups. Okay, we may have 3 or 4 groups in a study, and we want to see if those groups are different from one another. Okay, we will be using sample data, and the goal, as usual, is to draw a conclusion about the larger population. The clear advantage, the reason that the ANOVA exists, is because it allows us to compare more than 2 groups at the same exact time. If you remember back to the t-test, right, the most kind of complicated t-test we talked about was the independent samples t-test, where we simply have 2 groups. Okay, once we move beyond 2 groups, the t-test is no longer appropriate. And I'll explain why in a moment. But whenever you have 3, 4, or 5 groups, okay, or even more than that, you have to turn to the ANOVA typically to evaluate your data. Okay, so here's a typical situation for using an ANOVA. Okay, we have 3 different samples here that have been randomly drawn from 3 populations of interest, and we're looking to see how these samples perform. Okay, are they different from one another? And ultimately, can we make a larger conclusion about the population they've been drawn from? So you can imagine here that this is just a typical drug study. Okay, maybe sample 1 receives a placebo or a sugar pill. Maybe sample 2 receives a low dose of a certain drug. And then sample 3 receives a higher dose of a drug. Okay, and we're going to look for differences on some kind of outcome across these samples with the goal of being able to say, if all of these populations of interest were treated in the same way, the same kind of results would hold. Okay, does that make sense to people? Really, all we're doing here is just looking at another group, okay, more than 2 groups. So this is some terminology that comes up for the ANOVA. Okay, when there's an independent variable, okay, usually it's the variable that designates the groups. We call that a factor. Okay, that's ANOVA terminology. So in the previous example, okay, the factor was drug dosage. Let me just go back to that slide. Okay, the factor was dosage amount of the drug, ranging from placebo to a low dose to a high dose. Okay, that's our variable designating our groups. The level is the number of sort of conditions that exist in that factor. So how many levels were there to the dosage factor? 3, right? No drug, low dose, high dose. Okay, if we look back here, there are 3 different levels to that factor. So this is terminology that comes up. Okay, and the term factorial design, all that refers to is a study that's combining 2 or more factors. Okay, 2 or more independent variables. Sometimes we call them quasi-independent if they're things that we can't manipulate. Things like age and sex can't randomly be assigned by a researcher. Okay, so most research studies today are more complicated. We want to look at a couple of different factors. Maybe we want to look at drug dosage as well as sex. Does it matter if you're male or female? And see if there's some kind of interaction there on the outcome. So the ANOVA allows you to combine different variables not only to see how they directly affect some kind of outcome, but to see whether they interact with each other. Okay, so we can engage in more complex research designs when we're using factorial designs. Does that make sense to people? We're no longer looking at the influence of one single variable on one outcome. We may be looking at a multitude of variables. Okay. So here's just an example of a two-factor research design. Here, the researchers were interested in two factors, okay? Therapeutic technique and time, okay? Time over this different course. Okay, how are people performing before therapy, immediately after therapy, and then 6 months after therapy? Okay, so time is one factor, and it has 3 levels. Does everybody see that? Okay, time is a quasi-independent variable. We can't manipulate time. Okay, but we are interested in whether timing has an impact on this therapy's effectiveness. We're also looking here at therapy technique. Okay, so we have therapy method 1 and therapy method 2. This is another factor, and it has 2 levels. Making sense? Here, the researchers have some kind of prediction that maybe one of these therapeutic techniques is going to perform differently over time than the other. Okay, maybe both of these techniques work equally right after therapy, but one of them is maybe more robust long-term, and people who went through that treatment have more improvement. Okay, they have some kind of hypothesis that therapy and time are going to interact to influence outcomes on some kind of probably clinical disorder, some kind of set of symptoms, something like that. This is what we would call a 2-by-3 design. Okay, we have one factor with 2 levels, and we have another factor with 3 levels. This kind of design allows us to see how therapy influences outcomes. It allows us to see how time influences the outcomes, and it allows us to also look at what's called an interaction. Okay, do therapy and time interact? Okay, is one therapy more or less effective at different points in time? This is called obtaining main effects to see how one variable influences an outcome, as well as interaction effects, seeing how things combine, okay? How do they interact with each other? Okay, but these are the kinds of more complex research designs that you can use and engage in with the ANOVA technique to analyze the data. Okay, everyone following that so far? So here are our hypotheses for the ANOVA test. Okay, just like every single test we've talked about, we always need to state our hypotheses. Okay, in this case, the null hypothesis says that there's no differences across any of these groups. Okay, if I'm going to say that more formally, right, the level on the factor, the different conditions, do not affect the dependent variable. They don't affect the outcome. Okay, this means that the means across the different groups are not different. Okay, they're all the same. So to go back to this example, it doesn't matter what therapy technique you're exposed to, the results will be the same. It doesn't matter whether we measure you before, after, or 6 months later, there'll be no difference, okay, in the average scores across groups. Okay, as usual, the null is typically saying that, you know, there's nothing interesting going on here. There are no group differences. Can anyone guess maybe what the alternative hypothesis is? Yeah, there's a difference somewhere, okay? There's a difference between some of these groups. It may not be all 3 of them. Somewhere there is a difference between one group and the other. Okay, that's the alternative hypothesis. There's at least one single mean difference among the populations. Okay? Now the null can be wrong in a couple of different ways. It's possible that all of the groups are different. Okay, or it's possible that some groups are different from each other, but others aren't. Okay? If we have 4 groups, maybe 2 of those groups are different and the other 2 are not. Okay, so the alternative hypothesis is very low stakes. It's just saying there's one group that's different in this entire study, and we're trying to find out where that difference lies. So the statistic for the ANOVA is called the F test. Okay, we've talked about Z, we've talked about T. This is known as the F test or the F ratio. And this test is all about variance. Okay, we've been talking a lot about variance in here over the semester and how it's really important for our ability to detect effects. Because we have a multitude of groups in an ANOVA design, it's a little bit different or difficult to use like average differences when there's all these groups. So we're going to be instead looking more at variance for this test. And what the F ratio is basically looking at, okay, are the differences that exist between the groups. Okay, what are the actual differences in the data between these groups? And what are the differences we'd expect if the treatment has no effect? Okay, what's the difference we could expect if the null is true? Ideally, we have a very small denominator and a high numerator, and we get a large F result. Okay, and the math that goes into this is pretty tedious. There's a lot of steps, but this is basically what the F ratio is getting at, and I'm going to unpack this a little bit more here. Okay, so we have to move away from looking at mean differences when there's more than 2 samples. Okay, and we're going to be zooming into the variance that exists between each one of these groups. We want to have very small variance within each group, okay? We want people to be responding similarly to the different treatments they're in. So that's called the within subjects variance. Within each group, we want people to be responding consistently, right? If I give a low dosage of a drug and I think I know how it works, hopefully everybody's outcome is somewhat similar, okay? We don't have people getting better or getting worse, not changing, but everybody is moving in a predictable direction. Okay, so within each group, we want to have small variance, but we want differences between the groups to be big. Okay, so treatment 1 should be different than treatment 2 and should be different than treatment 3. So you might want to put in your notes or note down that for the ANOVA, we want the differences between groups to be really large. But within each group, we want people to be responding similarly. Put differently, we want the variation or the noise within each group to be low, because that means that our treatment or our intervention is having a predictable effect. Okay, here is the F distribution. Okay, it is a positively skewed curve. And here are your critical values. Okay, so for the 0.05 alpha level that we've been using in this class, you would need to obtain an F ratio of about 3.8, almost 4, in order to find a significant effect. If you bring your alpha level down to the 0.01 level, okay, that's the extreme 1%, you almost need about a 7 F ratio in order to have a significant difference. So I'm going to go ahead and I'm going to pass out these F tables. This is the reference table for the F test. I'm just going to give you guys a bunch more on what the extras. So F ratios around 0, 1, 2, and 3 are rarely significant. And as we get up, as we get higher F ratios, they tend to be more likely to be statistically significant. There really is no limit on the F ratio that you can get. Okay, this is cutting off here at 7, but you can obtain F ratios much higher than that. Again, it's all about the variance or the noise that exists within each group as well as across the groups. Okay. So you might be wondering, why can't we just use multiple t-tests, right, in order to look at more than 2 groups? If we have 4 or 5 groups, can't we just run t-tests every which way to figure out which groups are different? Now, remember the type 1 error? Does everyone remember that? What is a type 1 error?
Type 1 error is when you reject the null, even though it's not true.
Yeah.
It's not false.
It's a false alarm. You think that your treatment had an effect, Okay, you rejected the null and you shouldn't have. Okay, you really should not have thrown out that null hypothesis. Now, what's our typical risk of a type 1 error? When we set our alpha level at 0.05, right, that tells us that our risk of making that type 1 error is 5%. Everyone remember that? Now, that's for one single t-test. Okay, so if I have a couple of groups, okay, groups 1, 2, 3, and 4, and I run a t-test here, my risk of a type 1 error is 5% on that single test. Now, if I go to groups 2 and 3, I have another 5% risk of a type 1 error. Now, if I go ahead and run another test on 3 and 4, I have another 5% risk. If I contrast 4 from 1, I have another 5% risk. The problem is that across the entire experiment, we've now increased the risk of a type 1 error to 20%. Does everybody see that? We made it really high. Okay, because every time you run a single t-test, there's a 5% chance of a type 1 error, okay, maximum. The best thing about the ANOVA is that it evaluates all of those group differences at the same time in one shot, and it keeps the risk of a type 1 error at 5%. Okay, so we get all of the comparisons computed in one single analysis, and we don't have that problem of an increased risk of a false alarm, a false result. Okay, to say it formally, the ANOVA preserves our chance of a type 1 error. It keeps it at 5%. Okay, when we run individual t-tests, that type 1 error rate accumulates across each test, just like we saw over there. That's sometimes called the experiment-wise alpha level. Okay, does that make sense to people? So let's look a little bit more at the variance, okay, that's going on in the ANOVA. It's called an analysis of variance because we're zooming in and we're really analyzing and partitioning, okay, the differences that exist in the data. We're specifically interested in two kinds of variance, okay, the between treatments or the between subjects variance, and the within treatments or the within subjects variance. I've already talked a little bit about these, but I want to spend some more time on them because this is the core of the ANOVA test. When we look at the treatment between the groups or between the treatments, most of those differences can be attributed to the treatment, okay, the different intervention or the different treatment that that group's being exposed to. So we can be fairly confident that when groups have large differences, a good portion of that is because we treated them differently. Make sense? Somebody got no drug, somebody got a low dose, somebody got a high dose. Okay, and we can be fairly confident that if there are big differences between those groups, some of it has to be due to our intervention. The within treatments variance are the differences within each of those groups. Okay, and again, we want that to be small. Okay, when people are responding very differently to an intervention or to a drug, it means that that drug or that intervention doesn't have a predictable, consistent effect. We don't really understand how it works. It improves some people, it makes others worse. For some, it's neutral. We want our within treatments variance to be low. We want people to be performing similarly under different treatment conditions. When our within treatments variance is really high, when people are kind of responding chaotically in each one of our treatment conditions, it supports the null hypothesis, okay? That there really aren't any meaningful differences across these treatments. Okay, remember, high variability obscures patterns. When you have high variability within the groups, remember, it becomes really difficult to figure out what's going on. So if we're testing, we're using an ANOVA in a study, we're going to want our between treatments variance to be large. Okay, our groups are responding differently to the different conditions, but within each group, they're responding in a predictable, consistent manner. Okay, does that make sense to everybody? And that's what the ANOVA does. It quantifies the variance between and within groups, and it computes that ratio. Okay, this is just some hypothetical data from a study that is talked about in the text. Okay, in this study, they were looking at driving performance in 3 different conditions. So they were trying to see whether cell phones impair driving. Okay, so we have 3 different groups here. Okay, we have a treatment factor, and there are 3 levels. Okay, group 1 has no phone. They're driving down the simulated driving course without any phone. Group 2 is doing a handheld phone. And then group 3 has a hands-free phone. And we can count the number of mistakes that they make on the driving course. And then we can compute the mean. Okay, so the mean number of mistakes for not using the phone was 4, and then we had 1 and 1. Kind of like counterintuitive results. And sometimes in science that happens. Sometimes we get results that are surprising and maybe don't go along with what we predicted. But here, if you had a look at these 3 means, does one group seem different than the other? Right, group 1 seems to be making a lot more mistakes than groups 2 and 3, which are pretty equal in performance. Okay, so this is just another example of a kind of scenario where an ANOVA would allow us to determine whether these groups are different. Now, if we look at these mean differences, okay, these are our between subjects differences across the 3 groups. We want these to be large. But within each group, we want people to be behaving similarly. Okay, that's our within subjects variability. And it looks pretty good. Okay, most people in these groups where the number of mistakes is low, they're making relatively few mistakes. And in the group where the number of mistakes is high, they're making relatively more mistakes. It's pretty consistent. Can you guys see that? Within the groups, the response is consistent. Across the groups, we can see the differences, at least between groups 1 versus 2 and 3. So another way of thinking about this is systematic versus random differences. Okay, systematic differences are predictable effects of a treatment. Okay, they have systematic predictable effects. If we really understand how a treatment or an intervention works, it's going to have a consistent predictable effect. If I have some new kind of talk therapy for clinical depression, and we really have looked at it and studied it, and we know how it works, right? We should be able to predict on average how much it will improve people. Okay, if it's not performing systematically, if some people are getting worse, if some people aren't changing, then we don't really understand that treatment, and it may not be as effective as we thought it would be. Random unsystematic differences are usually due to individual differences. Okay, this creates noise in the data. It can be because the people are different. Okay, the people and the treatment conditions are different. They have different personalities. They have a different genetic background. They have different brains, different brain chemistry. They have different environments. Okay, there's a whole bunch of individual differences that can produce noise in the groups. And sometimes we have what's called measurement error. When we do experiments, sometimes error can creep in. Maybe something didn't go as precise or standardized in the study. Maybe the computer shut down and we had to restart it. Okay, maybe somebody didn't understand the questions they were being asked. Okay, that's called experimental or measurement error. But when we run our studies, we really hope that we have large systematic differences and that we can minimize noise. Okay, all this stuff is noise. And if there's too much of it, it's going to obscure our results. Does that make sense? And when you go on to research methods, for those of you who are going on to that class, a large focus for part of the course is when you run experiments, how can we reduce this random noise? Okay, there's a whole bunch of ways to do that. We can randomly sample people. We can make sure everybody's being studied and tested in the same environment. Okay, there's a whole bunch of ways for minimizing random noise. Okay, so this is basically what the F ratio is looking at in sort of normal terms. The numerator gives us the differences that exist between the groups, okay, that largely reflect treatment differences. So we want the numerator to be large. We want our treatments to have differences across different people. The denominator is essentially a measure of unsystematic effects, okay, noise that exists that's not due to the treatments. The treatments aren't producing that noise. A lot of this stuff is individual differences. It could be measurement error. It's the stuff we want to reduce. Now, if our denominator is small, okay, and our within groups noise is low, and we have big differences across the groups, we're going to get a large F ratio. Do people see that? And just like every statistical test, the larger your outcome, the more likely it is that it's statistically significant. Okay, just to put this in one other way, the numerator of the F ratio, okay, the bigger that is, the more support you have for the alternative hypothesis, right? That the treatments produce different effects in the groups. If the denominator is really large, that supports the null hypothesis, okay? That these differences are all over the place and they're not even due to the treatments. Does that make sense to people, that logic? Okay, this is just a visual capturing the same exact idea. So what the ANOVA is allowing us to do is say, hey, this is the total amount of variability present in the study. Now we're going to partition it. Okay, here are the differences that exist between the treatments. Most of this is caused by systematic treatment effects. Some random noise can get in there, but it's minimal. Overall, when we have differences between groups, we can be somewhat confident that it's due to our treatment. And we're going to compare that with the within treatments variance. Okay, how different are the people responding within each group? Most of that is due to random noise and unsystematic factors. We want this to be maximized, and we want the within variance to be minimized to have the best chance of a significant result. Okay, and that's why this test is called the analysis of variance. We're literally analyzing these different kinds of variance and computing a ratio to see which one sort of wins out. Everyone pretty good on that? Yeah, that's like the logic behind the test. Okay, if the null hypothesis is true, that means that our treatment effect is going to be near 0, and we can expect to get F ratios of about 1.0. Okay, so F ratios around that 1.0 mark usually mean we don't have enough evidence to reject the null. There's no detectable treatment effect here. If the alternative hypothesis is true, okay, it means that we do have a treatment effect, and we're usually going to get F values well above 1.0. Another way to think about the denominator of the F test is that this is a measure of error. Like every statistical test we've conducted in here, that denominator is always, right, standard error, some form of error, some form of noise that we want to minimize. Okay, so some people will refer to the denominator of the F ratio as the error term. And we always want to reduce error in our research. Okay, so I want to go ahead, I want to show you this example. This is a cool video. It's just a couple of minutes. It's a guy kind of explaining another research situation where an ANOVA test would be appropriate, and he unpacks this variance again. This is conceptually really important to just understand what this test is getting at. Okay, so the first question here is asking whether this is true or false. The ANOVA allows researchers to compare several treatment conditions without conducting several hypothesis tests. Everybody should be saying true to that, right? It's one single hypothesis test. We can evaluate the differences between all of the groups in one shot while minimizing and keeping consistent the type 1 error risk. Okay, the other one, if the null hypothesis is true, the F ratio is expected to have a value of 0. Okay, this is actually false. Typically, when the null is true, we're going to get F ratios of about 1, right? Which means that the between subjects variance and the within are basically identical, and we're getting a result of 1.0. That supports the null hypothesis. So if you were going to go ahead and compute an ANOVA by hand, there's a series of stages that you have to go through. Okay, and I will post a worksheet that will show you how to compute each one of these results in order to get the F ratio. But again, my focus is more on you understanding what this test is doing and being able to understand the statistical output coming out of the software. Okay, but there's a couple of different computations. Okay, it involves calculating sum of squares, the entire study, between and within the groups, then going on and computing something known as mean squares, the total study, between and within the groups. Okay, these are going to give us our measures of variance in order to get the F ratio. And it's just a series of simple calculations, but it's just, there's a lot of steps to it, and they're just kind of tedious, like I said. Okay, but I will put that worksheet up there if anybody wants to look at it and try to do one on your own time. Okay, and I've even included a video here. This video shows you somebody calculating an entire ANOVA from A to Z. Okay, it's about 12 minutes long. I'm not going to play it in here, but if that's something of interest to you, you can check it out. Okay, but basically, it's just time consuming. Okay, so let's go ahead and look at how we would run an analysis of variance actually in some statistical software. Okay, which is exactly what you guys are doing. Okay, let's go ahead here and move into looking at effect size for the ANOVA. So now that we know a little bit more about the F test, we can accompany it with a measure of effect size. Okay, and just a heads up in terms of this table, okay, this is just the critical table for F values if you need to look one up. Okay, so up top is the degrees of freedom, number 1. That's just the number of groups minus 1. It's signified as K minus 1. So if I had 3 groups, my degrees of freedom up top here is 2. Okay, you can just write up there if you want, number of groups minus 1. Going down the side, we have our second degrees of freedom. That's simply the number of subjects in the study minus the number of groups. So if I had 25 people and I had 3 groups, it'd be 25 minus 3, 22. That's where those values are coming from in parentheses on the board from the example we just did. So we would look at, let's just go ahead and do an example here. If we find on the top row the degrees of freedom of 2, and then we go down to 22, okay, on the left side, okay, what is the F ratio we would need for significance? People seeing that? People seeing 3.44? That would have been the F ratio we would have needed to get in that example for significance. We didn't get that. Okay, we fell short of that 3.44. So just that's how you can look up the critical value on the F table. There's 2 degrees of freedom to keep in mind. Okay, up top is the number of groups minus 1. And going down on the left side, it's the number of subjects minus the number of groups. So if I had 25 people in 3 groups, it'd be 25 minus 3. N minus K is the way you would write that out, like in scientific notation. Makes sense to people? Then you match it up and you find the critical value. Okay, here's eta squared. Eta squared is our measure of effect size for the ANOVA. And it's simply some basic division between the sums of squares. Okay, we have the total sum of squares in the denominator and the sum of squares between the treatments. Remember, sum of squares is an indicator of variability, right? Spread in the data. It's the sum of all of the square differences in the data. Okay, if we have a really, really large sum of squares between our groups and a really small total variability, right, we're going to get the largest eta squared. That's going to be a large effect size. Okay, so simply put, we want our differences to affect those groups different. Sorry, our treatments to affect those groups differently. So if you ever see this symbol, this is just eta squared. And when people report the results of the ANOVA, they typically will accompany it with an eta squared. Okay, it's similar to R squared. It gives us the amount of variance explained. Okay, how much does the group predict the outcome? And we can convert that into a percentage. And for some reason for ANOVA, we call it eta squared. Okay, because it's computed a little bit differently. So this is just an example of in the literature. Here's another one. If you're doing the stats project and you forget how to write up the F test, here's a model. In our question, you didn't have to compute effect size. Okay, but here's an F test with 3 and 20 degrees of freedom. So there were 4 groups, right? And there were 23 people. F came out to be 6 and change. Here, the researcher has noted that the probability of a type 1 error is below 1%. They chose to use that more strict conservative value. And then they followed up with a measure of effect size. This is saying that about 50% of the outcome can be explained by the groups, the different groups, okay, and the treatments they were administered or the interventions they experienced. Okay, this is just a visual capturing this variability point one more time. This is really the key takeaway point today. The ANOVA is all about variability. Here's an experiment where we have two treatments being compared to each other. Can you see how the groups look really different from each other, right? There's a consistent predictable difference. Everybody in treatment 2 is scoring higher than those in treatment 1, and there's a clear pattern that emerges here. The between treatments variance is low here, or is high here. Okay, these groups are very different, but within each group, people are responding similarly. This is what you want if you want to be able to draw a conclusion and find a significant effect. Okay, it's easy to see treatment 2 produces higher scores than treatment 1. Down here, it's the complete opposite. This is riddled with variability, okay, within the groups. We have people from treatment 1 scoring high, low, and in between, and the same for treatment 2. We don't know how these treatments work. They don't give us predictable results. Okay, if I expose you to treatment 1, you could land anywhere, all over the place. We don't really understand these treatments. A situation like A up here, you're likely to get a significant F-test. Down here, probably impossible because all of the noise within the conditions is going to wash out your F ratio. You're going to be dividing by a really big denominator. Okay, so I just wanted to put that up there because it's a visual of what that ANOVA test is getting at. Okay. Here's a little information on those post hoc tests. We've already looked at one. Okay, Tukey's test is called the honestly significant difference test. All it's telling us is which groups are different. Okay, just because our F ratio is significant, it doesn't tell us which groups are different from another. Post hoc tests are follow-up tests that tell us which groups are different and which are not. Now, the thing to note with post hoc tests is there's a whole bunch of them out there. The Tukey's test is the most common, but there's a whole bunch. You can actually you can take a course on post hoc tests. Okay, there's a book on all of the different post hoc tests that exist. Depending on your data, different ones are more or less appropriate. Okay, this is the Tukey's test that we just ran in StatCrunch. Okay, this is just computing. Again, just focus on the big picture. It's telling us which groups are different. Another post hoc test is the Scheffé test. This test is really strict and conservative. Okay, it's a little bit more difficult to find a statistical effect because it's a very safe, conservative test. The way this is calculated, it's a little bit more difficult to say that groups are different from one another. So depending on what field you're in and what research you're doing, certain post hoc tests may be more or less common. You really need to know what area you're researching and what the norm is. So this is just a slide here, just comparing the T distribution and the F distribution. So we had been working with T for the past couple of classes. We've now moved on to the F distribution. Okay, and you can see it's positively skewed, and we're typically looking for results in this positive tail. Okay, our alpha level is going to set sort of the strictness of how big our F ratio needs to be statistically significant. Let me just pause this.